All right, starting in chapter 1, we're going to look at the idea of functions, domains, and ranges. These are things that we have talked about before in the past, but we're going to go through it really quick because when dealing with calculus, you're dealing with functions all the time. You're going to be dealing with a lot of functions. You're going to have to look at the idea of domains, ranges, and work with the domains and ranges, and just know the terminology, what is meant by domains, ranges, functions. When we were in trig class, we said a relation was a set of ordered pairs. Okay, a set of ordered pairs. Now we can signify the set of ordered pairs as an actual set. We can write it as sets, and that would give us a set of ordered pairs. We talk about a group, a set, we're looking at just a group of ordered pairs. But when we're talking about a set of ordered pairs, we can also take a look at an XY coordinate system in our graph. Because on this graph of this line here, if we continue to slide on indefinitely, how many points exist on the line? How many points are on the line? An infinite amount, okay? So with every one of those points, we have an ordered pair. Each one of those points has an x coordinate and a y coordinate. So we have an infinite number of points here as we go along this line, which means we have an infinite number of ordered pairs that go on this line. So we can symbolize a relation also by looking at a graph. Okay, we can look at the graph because on this graph, we have an infinite set of points, which gives us an infinite set of ordered pairs. Which we've also talked about when we look at a graph, that's also a solution set to a two-dimensional equation, an x and y equation. A solution set to the equation solving that equation. Okay, the domain. Domain is defined to us as a set of all first values of the ordered pairs of the relation. Most of the time in the algebraic world, we're dealing with the first values of the ordered pairs are typically x. But it can be anything that you want that's going to be the first value of the ordered pair of the relation. It's going to be your horizontal axis variable. Whatever your horizontal axis is, that is your domain value. And once again, algebraic world, we deal with x a lot. When you get into the scientific world and what we'll talk about in physics, there's going to be time here. There's going to be the horizontal graph. The reason why we have calculus, let's go back just for a second. The reason why we have calculus, we work with calculus, was you have two people that invented the idea of came up with the idea of calculus. One was Gottfried Leibniz, and one was Sir Fig of Isaac Newton. And there's sort of a little friction between these two guys. Sir Fig of Isaac Newton developed all these scientific principles, physics. Sir Fig of Isaac Newton developed physics and all the concepts that goes with physics. Leibniz sort of developed also the same, but was not quite in tune with Sir Fig of Isaac Newton. So there was a little friction in regards to Leibniz and Newton. But what Newton wanted to do is he wanted to have a mathematics that explained physics. And we talk about the idea of calculus. Calculus is the mathematics that explains physics. All the things Sir Fig of Isaac Newton came up with and all the developments in physics, they needed to have a math that explained it. So calculus was developed. So they say Leibniz and also Newton were the fathers of calculus. It's more Sir Fig, but Leibniz has some contributions there. Once again, they're not quite on the same page, but the combination of both of them developed the idea of calculus and what we talked about with respect to calculus. When we talked about a domain, it's your horizontal axis. It's your x variable typically. When you get into the physics world, there's going to be a lot of t's there, time, that we'll be dealing with. The range is a set of all second values. The set of all second values of the ordered pairs of relation. Typically, this is y. Vertical axis. The independent variable and the dependent. Variable. You can think of them that way also. The independent variable is a variable that you sub in. The dependent variable is a value that is a result by you subbing in the independent variable. A relation or a function is a relation such that each value from the domain corresponds to exactly one value from the range. Each value from the domain corresponds to exactly one value of the range. And that's the idea of a function. When we talk about a rule, see here's rule. A rule for a function assigns to each number in the domain one and only one value in the range. This is for a function. For a relation, it can go to multiple values. But for a function, it assigns each value in the domain one and only one value in the range. Just for reference, here's Gottfried Leibniz. He was born in 1646, died in 1716. Sir Fig of Isaac Newton was born in 1642, 4 years earlier, and died 9 years later in 1726. But Leibniz was the only notable mathematician produced by Germany in the 17th century. He was a philosopher known for his belief that this is the best of all possible worlds, an idea that was later saturnized by Voltaire in the novel Candide. I don't know, it's beyond me. The most outstanding contribution Leibniz made in mathematics was his discovery in 1675 of the fundamental principles of infinitesimal calculus. Newton had invented his own system of calculus in 1666, 9 years earlier. So Newton developed 9 years earlier his own system of calculus. Gottfried Leibniz in 1675, 9 years later, developed fundamental principles of infinitesimal calculus. But Leibniz published his findings 9 years before Newton's system appeared in print. The two systems differed in notation, but some charged that one man had derived the basic idea from the other and just invented another notation for it. Like I said, there's a little friction there in the math world. There's drama in the math world between Leibniz and Newton. Okay, today it's recognized that both two men were made independent discoveries. Leibniz's system proved superior to Newton's and was later adopted universally. Among his accomplishments was the invention of a machine capable of multiplying, dividing, calculating the square root. Okay, he invented the first calculator. the idea. It was more of an adding machine that did it. A machine that did that for him. Leibniz also introduced and developed much of the notation which is used today, including the decimal point, equal sign, the colon to indicate division, and ratio, and the single dot to indicate multiplication. So Leibniz, there's some gray areas there. Who developed too? They said Newton may have discovered it first, and Leibniz just changed some of the notation. But Newton didn't publish any of his mathematical ideas till later, so there was no like copyright to it at all. That you could say, well, that was plagiarism. He plagiarized Sir Fig of Isaac Newton. Newton was an English mathematician, physicist, and astronomer. His family intended that he devote his life to farming. Sir Fig of Isaac Newton was supposed to be a farmer. Instead, he became probably the most brilliant mathematician the world has yet produced. Newton produced the laws of gravitation and the Principia, which is considered the most influential and most admired work in the history of science. His other great accomplishments was the invention of an integral and differential calculus. Hating controversy, Newton was reluctant to publish any of his findings. Almost all of his ideas remained unpublished for years. This caused problems, the greatest of which was a dispute between Leibniz over which man was the true originator of calculus. Newton seemed to have been working on it first, but published his findings later after Leibniz. Apparently, the two men created their own systems independently of one another. Despite such arguments, Newton was a modest man, generous to those who helped him in work. He credited with saying, "If I have seen a little further than others, it's because I stood on the shoulders of giants." So, once again, there was drama in the calculus world back in the 1600s on who really did what. So they just classified Leibniz and Newton both as the fathers of calculus. They give them both credit because they both had contributions that are there. Well, we have Euler notation when we're dealing with functions. How can we signify Euler notation in terms of function? Well, we're Americans. Okay, we look at that and we say that's Euler. But if you're a German, okay, that's going to be Euler. That's going to be Euler. Let's see if I can find Euler here. Here's Leonard Euler. Born in Switzerland, without a doubt the most productive mathematician of the 18th century, he studied under Johann Bernoulli in the University of Basel, obtaining a master's degree. Okay, he obtained a master's degree at age 16. Where are you guys at? Come on, 16 years old. Where are you guys at? You should be way beyond my class right now and have your master's. Euler followed Bernoulli and two sons to Russia, where he taught mathematics and physics at the St. Petersburg Academy in a lifetime devoted to work in both pure and applied mathematics. Euler wrote more than 800 books and papers. He made contributions in virtually every branch of mathematics that was then known. In his popular and prestigious textbooks, Euler succeeded in clarifying, expanding, summing up, and ordering all the work of his predecessors. So he took everything from behind and sort of organized it. Euler's writing included the first text of analytical geometry. His work in trigonometry offered concepts and notations that are still used today. We're going to go through one here with Euler notation. In algebra, several equations bear his name. After losing his sight in one eye at age 25, Euler became totally blind later in his life, but continued writing, dictating ideas from his remarkable memory. So we want to be able to write things in Euler notation. Okay, when we talk about Euler notation, y is equal to f of x, g of x, h of t, It is a function notation. We replace the y with function notation or Euler notation. Once again, this value right here, this is the independent variable. This is your independent variable within the parentheses. The function values, the letters outside, that gives you a function value. That is basically your y value. So your ordered pairs then change from x and y to x and f of x. So we have our dependent variable, our independent variable, and our y value. This right here, once again, what we talked about here, for a function assigns each value from the domain one and only one value in the range. This here is your rule. It's your equation. It tells you, okay, we're going to take a value from the domain. We're going to take a value from the domain and give it this value in the range. And how do we do that? Well, we have a rule of x squared plus 5. So if I find my function value of 4, here's my x value. I'm going to run it through the rule of x squared plus 5 and come down to what, Jacob? 21. Where we have 4 squared plus 5, or a value 21. So if I wrote an ordered pair, my ordered pair would be 4 and 21. Domain is a set of all first values of the ordered pairs in a relation, the set of all usable. It's also, we can also classify this as the set of all usable values for the independent variable. What are the usable values for the independent variable? What are the values that make the function defined? And we exclude the values that make the function undefined. So this is your idea of a domain. What values make this function defined, and we exclude the ones that don't. So if I have the square root of x minus 4, square root of function value, the rule is the square root of x minus 4, and I want to find the domain. What has to be true about the value underneath the radical to keep it in the real world? Has to be what, Justin?
Can't be negative.
Can't be negative. It has to be positive or 0. Okay, cannot have negative there, because if we use a negative in there, that's going to put us into the Barney world, and we're into the imagination. Okay, so we can't get into the imagination world, in the Barney world, so we have to make sure that this is not negative. So it can be 0 or it can be positive. Well, how can we write that in an inequality? Is this x minus 4 has to be positive, so it has to be greater than, or it could be equal to a value of 0. So now we have an inequality we can solve. Hopefully we can solve this by adding 4 to both sides. So x is greater than or equal to 4, and then we want to write this back into our interval notation. X is greater than or equal to the value of 4. It's an unbounded interval. We started at 4. And we can make it to infinity and beyond. And we have it closed at 4 because we can include the value of 4. So we can have our radicals. We can have rational expressions. What do we have to watch out for with the rational expressions here? Sydney, what do we not have?
A negative on the bottom.
We got negative on the bottom, but it has something to do with the bottom. What can we not have on the bottom?
0.
0. So this x plus 4, cannot equal the value of 0. Can the top be equal to 0? Yeah. We can take 0 divided by 5 and get 0. But if I have 5 divided by 0, I get an error in my calculator. So x not equal its value of negative 4. Now there's 2 methods of madness to be able to write a solution. We can go from negative infinity to negative 4 and open it at negative 4, not include it. Union negative 4 to positive infinity and beyond. Or people tend to veer towards this a little bit more. Negative positive infinity, comma, x cannot equal negative 4. All right. Determine the next two domains. What would be your next two domains? Check your answers with somebody around you. Just the first one.
X negative infinity to positive infinity, and then x cannot equal negative 4 and negative 1.
Negative 4, negative 1. We can factor this down to x plus 4, x plus 1, not equal value 0, so we have negative 4, negative 1. We have a combination statement here at the very last one here. Okay, we have x minus 3 over square root of x plus 4. Okay, what do you have for this one?
I didn't know if the radical sign was like the full radical sign or not. Is it just on the x?
It's over the x plus 4.
Oh. X is a number of negative infinity, negative 4.
Negative infinity, negative 4, because this x plus 4 has to be greater than the value 0, correct? So we can subtract 4. So if we subtract 4, what's our solution?
X is greater than negative 4.
X is greater than negative 4. Can it equal 0? Well, on the top one, we had a radical that could equal 0, but can we equal 0 on this one? Why not?
It's on the bottom.
Because it's on the bottom. We can't have 0 on the bottom. Over here, this can't equal 0. So over here, this x plus 4 just has to be greater than the value of 0, because if it equals 0, we can't have 0 in the denominator. So it's sort of a combination of things. So if we take a look at my solution here, we have to be greater than a value of -4. So our solution would be what?
X is a member of 4 positive infinity.
Okay, -4 to positive infinity. And we cannot include that because we can't equal the value of 4. Because we can't have 0 on the bottom, or be at value -4. Okay, we take a look at our graphs. We look at our domain. Once again, we have a set of ordered pairs here, but it's all embedded within a graph. What would be your domain for this one here? Do we have anything, any values of x that we don't use in our graph? What would be your range values, your y values? Then what's your domain?
Me?
Yeah.
Sorry, negative infinity to positive infinity.
Negative infinity and positive infinity, because we use all the x values here. Our range values, Justin?
-2 and 2.
Now, if we take a look at our graph, it sort of looks like it touches the 2 and -2. So I'm going to throw the brackets in there because it looks like we touched. But if you sat there and said, I'm not quite sure if it touched it or not, and you have parentheses in there, okay, that I would probably go with that. I'd be fine. Is this a function? What do we use there, Jacob?
Vertical line test.
Vertical line test. Let's go to the bottom one down here. I want to make sure I get to the last problem here. Let's go to the bottom one. These lines go on, these graphs go on indefinitely. What would be your domain and range for the side wave parabola? And once again, check your answers. Each other. Check way after domain.
X is a member of 1 to positive infinity.
Did you include 1?
Yeah.
All right. Put a bracket in there. Range. What do we have for range? Justin.
Negative infinity to positive infinity.
Because those will extend up and down. This is vertical, or as a function said.
No.
No. Because once again, we have a vertical line test. I have one specific x value, which is a value of 4, that goes to two different y values. We have y1 and y2. So we have one x value that goes to two y values, so it's not a function. Last thing we're going to look at is a difference quotient. We did this a little bit in pre-calc. It measures the average rate of change of a function. It's the measure of the average rate of change of a function. Now, where you will see this is when we get into, we're going to eventually get into what is called derivatives. okay? We're gonna go through limits here in chapter 1, but then we're gonna go into what is gonna be called derivatives in chapter 2, which is the main essence of calculus 1. We get into antiderivatives eventually, but derivatives is the main essence. The definition of a derivative is directly related to the idea of a difference quotient. So we're going to go back and review the idea of a difference quotient first. And this is just a delta y, and this is just a delta x here. So when we have one value divided by another value, it is a rate. We're talking about a rate here. So it's a measure of the average rate of change of a function. And it's defined to us as f of x minus f of a over x minus a. So our function here is f of x equals x squared plus 5. So to evaluate our difference quotient, we have our f of x, which is x squared plus 5, minus f at a. Well, our f at a is, well, if I have f of x, I had x squared plus 5, so if I have f of a, this would be a squared plus 5. All I'm doing is plugging in for a. And this is all divided by, I don't have to do any subbing on the bottom, x minus a. Now it becomes an algebraic rational expression for you to simplify. We distribute our negative sign through. We have x squared plus 5 minus a squared minus 5 over x minus a. Nice thing about constants is they cancel out with the difference quotient. So these are gone. At the top we have the difference of perfect squares. We have x squared minus a squared, which would factor to what? What would be our two factors here? And x minus a still on the bottom. X squared minus a squared factored down. What would that factor to? Difference of perfect squares. So two factors. Very quick, what's the two factors?
X plus A, X minus A.
X plus a, x minus a. The x minus a's, whoopsie, I hope I write it correctly. The x minus a's is a common factor top and bottom, so we can cancel them out. And we're left with x plus a. This is called your difference quotient. Once again, once we get into definitions of derivatives, we're going to come back to the difference quotient and utilize it a little bit more. Right now, we're just going to practice with respect to the difference quotient. All right, basic fundamental ideas of functions. Going through the ideas that we've talked about before with respect to functions. We will continue to utilize everything that we worked on here as we go forward in chapter 1. We'll start taking limits of functions, and we'll look at the idea of limits. Once again, all new material for you. Homework on page 19 to 21. You have some problems there, some various problems to deal with. All right, questions you have? All right, the rest of the time is yours.